Okay, so let me remind you a little bit of what we've done with the electrons, where we said, okay, we have a transmission coefficient at k equal to 0, so electrons going straight through. And then we have said, well, we might have a transverse dispersion where the electrons can also go at an angle. So now let's look at a dispersion of these transmission coefficients. Okay, so the resonances would be on this dispersion curve. And for electrons and gallium arsenide, the thing looks rather parabolic. Okay? All right, that means that transmission coefficient is roughly just a translation in energy, up in energy, along that parabolic dispersion. Now for holes, things are very different. So I've shown you the transmission coefficient on the bottom left on the previous slides. That's the transmission coefficient that sort of made sense as an aggregate coming from light holes, heavy holes, and split-off band. But if you now start to look at the transverse direction of these holes, you start to scratch your head. It looks very unintuitive, right? Nothing like a parabola. I'm going to try to sort some of these things out in the subsequent slides. But the things I like to highlight is that you start out from the gamma point on top of the valence band, you move down, and then you have an inflection. Actually, if you look carefully, you could think that this parabola could connect into here. Right? There's a sort of an anti-crossing there. The next state down, the light hole 1 down, it actually goes up in energy. What's going on there? I thought dispersions go down for holes. This one goes up. In fact, you could argue it kind of starts to anti-cross. It goes up and turns into a heavy hole state and goes back down. There's an anti-crossing there. And then this heavy hole 2 just goes down, and it has another anti-crossing further down with another heavy hole 3 state that seemed to have gone up. Right? I see a lot of puzzled faces in the audience. Good. I mean, this has been understood in the literature. It's not that this is the first time this has been looked at, but I'm going to try to sort out where these dispersions come from. Now, I'm going to do a dirty deed, right? I'm going to take a cut here at roughly the same momentum space. I'm going to show you a transmission coefficient here at 0.04 momentum, normalized momentum. And what you see is that that transmission has nothing to do with a transmission at k equal to 0. It looks radically different. So if you could assume, or had hoped, you could do a 1D integration where you could shift the transmission on the bottom left down in energy parabolically, because, you know, after all, everything is parabolic, you're completely screwed. Okay? All right. So now where does this complicated dispersion here in the middle come from? I mean, this looks really bizarre, right? This can't possibly be right. I mean, this is so wrong, it's not even false. So, if you look at experimental data tables, for gallium arsenide, you find that the gap at room temperature is 1.424, and the split-off coupling is 0.34. The effective mass at gamma is 0.067. And then you find tables that look like this. There is a light hole band, a heavy hole band, and a split-off band. And there's masses associated with that. And these masses have different values in different directions. Remember that slide I showed you, a crystal not looking quite symmetric in all crystal directions, and orbitals not quite the same in all crystal directions? Well, it comes out for holes in spades. It really comes out. What you see is that the effective mass here of the light holes goes from 0.87 in one direction to 0.78 in another direction. Not a whole lot of variation, but some. But boy, look at this heavy hole. In the 1001 direction, the effective mass is 0.4. In the 110 direction, it's 0.8. A factor of 2 difference. Remember your particle in a box where the lattice the spacing of the eigenenergies is dependent to the inverse of the effective mass. Right? You make the effective mass heavier, your states get a little bit closer. Well, they get a little bit closer by a factor of 2. Not a 10% effect or something. 2. On the right column, what I'm showing you here is the parameterization of our tight binding model that we use in this calculation, where we get the gap right, we get the split-off coupling okay, the effective mass in the conduction band, and we're doing all right with these masses. We're not doing extremely well. This is an sp3s star model. This work was done before we started to use the sp3s star D5 model. So down the line, we discovered for ourselves that really you need the d orbitals to do the valence band right. So what I'm going to show you now is done without the d orbitals, but I'm just going to show you what the physics is. But really the trends are similar. So the light hole mass varies a little bit, roughly by 0.01. And actually the heavy mass, we overestimate the fluctuation as a crystal direction, right? We start at 0.41 and get it 0.87 versus 0.4 to 0.81, okay? We're not doing quite right, but we're having the right trends. All right, so what does all that mean? So let me plot, pardon me, a light hole and a heavy hole dispersion in a two-dimensional space in kx and ky. Okay? So the light hole looks roughly cone-like on the tip, and you can see that it's a little bit asymmetric because it is rounded here. Okay? The heavy hole one is almost looking roundish on the top, but then it has almost square-like behavior, right? In the 1, 1, 0 direction, so in this plane here. So this is the 0, 0, 1, and this is the 0, 1, 0, kx and ky. There seems to be a ridge, right? Why is that? Because the effective mass for the heavy holes in the 0, 1, 1 is heavier than the effective mass in the 0, 1, 1 is heavier than 0, 0, 1. Okay? Meaning, in this direction, in the normal kx plane, the mass is light, so it shoots down, versus in the diagonal, it's heavier, it doesn't go down as fast. Okay? So now, we have gone through these explanations where we say, well, we have a man-made resonator of length L. Let's pick out the appropriate k, because we quantize k, right? So let me show you how some of these cuts would be like. So I'm going to take the light hole dispersion here, and we're going to quantize it at kz, well, I just plot kz equal to 0 here, then kz equal 0.04, and kz equal to 0.08. Those are the solid lines. You already see that those are not parabolas anymore. Okay? But you could argue if I pick a kz quantization, I make my box normalized to this size of 0.04, this is where the resonance energy would move in that k direction. That would be my transverse k direction if I quantize my resonator at 0.04. The excited state would be at 0.08, and it would move like this heavy line under there. Right? It wouldn't move parabolically, but it wouldn't look really crazy either. Okay? I mean, it looks almost parabolic with an increasing mass, right? But nothing really bizarre looking yet.